Assalamu alaikum. Welcome to this online lecture series of data mining, and this is our third lecture on the topic of association rule mining. In this lecture we will cover some efficient pattern mining methods, including a priori algorithm and some extensions and improvements of the a priori principle, which includes the how to reduce the number of passes of transactions database scans, in which we will discuss an extension of a priori principle which is known as partitioning methods. And the second measure is shrink the number of candidates to be generated. So in this point of view we will discuss direct hashing and pruning method, and for exploring special data structures we will discuss eclat. Okay, so as far as the summary of the previous lecture, we have discussed the basic concepts of pattern discovery and association rule mining, as well as we have discussed some applications of pattern discovery and what is the motivation behind studying association rule mining. And we also discuss about what are item sets, what are frequent item sets, frequent patterns, and what is sport, what is confidence. And after that we will discuss compressed representation of frequent patterns, in which we will discuss about we have discussed about closed patterns and max patterns, and after that we have discussed about the downward clear property of frequent patterns. So as we know, as we already discussed, that association rule mining is a two-step process. The first step is we have to mine frequent item sets from the transactional database, and after mining frequent item sets we can generate association rules from those frequent item sets. So there are different algorithms for mining frequent item sets from transactional database, in which we have two very famous algorithms. The first one is Apriori algorithm, and the second is FP growth algorithm, or frequent pattern growth algorithm. After mining the frequent patterns using any of these algorithms, we will try to generate association rules from frequent item sets generated by Apriori algorithm or frequent pattern growth algorithm. So in this lecture we will cover the Apriori algorithm. So this Apriori algorithm is proposed by Agarwal and Srikant in 1994 for mining frequent item sets for Boolean classification, Boolean association rules in AS94B. The name of the algorithm is based on the fact that the algorithm uses pure knowledge of frequent item sets properties, as well as we shall see later. So a key concept in a priori principle is to assume that all subsets of frequent item sets must be frequent, and similarly for any infrequent item sets all of its superset must be infrequent. So this algorithm is at the first candidate generation and test approach for frequent pattern mining. It is a level wise candidate generation test approach. A priori principle or a priori pruning principle indicates that if there is any item set which is infrequent, its superset should not be generated or even tested. So a priori principle can also be defined by another way, that all non-empty subsets of a frequent item set must also be frequent. So the algorithm, a priori algorithm, works as follows. Initially the first time you just scan the database once to get frequent one item set. Then taking this frequent one item set, you are going to generate length 2 candidate item sets, and at the kth iteration you are going to take a length k frequent item sets to generate length k plus 1 candidate item sets. So then you go against the database on database to test these candidates generated and to find the frequent k plus 1 item sets. Okay, at every iterations you just set the k to k plus 1, so you can go on and on until no frequent item set will be generated or no candidate item sets can be generated. Okay, then after you exit from the loop, you just return all the frequent item sets drive. That's the algorithm. So if we summarize this a priori algorithm is that at the first iteration, जब हम फर्स्ट टाइम डेटाबेस को स्कैन करते हैं तो हम वहाँ से फ्रीक्वेंट आइटम सेट्स गेट करते हैं। वो फ्रीक्वेंट आइटम सेट्स वो होती हैं जो कि हमारे मिनिमम सपोर्ट काउंट को फुलफिल कर रही हों, और जो रिमेनिंग आइटम सेट्स होती हैं जो कि मिनिमम सपोर्ट काउंट से कम हो उनकी अकरेंस या फ्रीक्वेंसी, उनको डिस्कार्ड कर दिया जाता है। और देन उन फ्रीक्वेंट आइटम सेट्स फ्रीक्वेंट वन आइटम सेट से हम लोग फ्रीक्वेंट टू आइटम सेट कैंडिडेट्स को जनरेट करते हैं कि उस फ्रीक्वेंट वन आइटम सेट से कितने कैंडिडेट्स जनरेट हो सकते हैं। सो उन कैंडिडेट्स को देखते हुए हम लोग उनमें से अगेन फ्रीक्वेंट टू आइटम सेट जो पैटर्न्स हैं वो जनरेट करते हैं। सिमिलरली उनमें से जो मिनिमम सपोर्ट थ्रेशोल्ड से कम होते हैं उनको डिस्कार्ड कर दिया जाता है, और जो मिनिमम सपोर्ट थ्रेशोल्ड को फुलफिल कर रहे होते हैं उनको हम लोग फ्रीक्वेंट टू पैटर्न कंसीडर करते हैं। सो फिर उन टू फ्रीक्वेंट पैटर्न आइटम सेट्स को से कैंडिडेट 3 आइटम सेट हम लोग जनरेट करते हैं, और एंड ये प्रोसेस कंटिन्यू रहता है जब तक के कोई न्यू फ्रीक्वेंट और कैंडिडेट सेट जनरेट ना हो रहे हो। और एट द एंड ऑफ दिस एल्गोरिथम हम क्या करते हैं, जो हमने फ्रीक्वेंट पैटर्न्स या फ्रीक्वेंट आइटम सेट्स ड्राइव किए होते हैं वो हम रिटर्न करते हैं। ओके, ये था ओवरऑल एल्गोरिथम। So let's look at the pseudocode of this algorithm. Suppose we set C sub k to be the candidate item set of size k, and F sub k is the frequent item set of size k. Initially we just get a frequent one item set, then we get into the loop. Suppose the frequent k item set is not empty, then we get in and we use kth frequent item set to generate k plus 1 candidate item set. Then go against the database using the minimum support to see which k plus 1 candidate item sets are frequent. So using those frequent k plus 1 item sets, we drive the frequent k plus 1 frequent item sets. Okay, then we reset the value of k to k plus 1 until we get out of this loop. We just return all the frequent k item sets for all the cases drive. Okay, so let's understand this working of the a priori algorithm with an example. Suppose we have a transactional database TDB which contains 4 transactions, and the transaction IDs for these transactions is 10, 20, 30 and 40. And the transaction 10 contains 3 items which is A, C and D. Similarly for transaction 20 and 30 and 40 we have different item sets in different transactions. And suppose we set the minimum support threshold to 2. That means any item set that occurs 2 times or more than 2 times in these transactions are frequent item sets. or in other words, if any item set that appears less than 2 times is infrequent. So on the first scan of the database we get C1 candidate 1 item sets. That means A item set has port count of 2, as you can see in the transaction database, A 1 and 2. A occurs only 2 times in the transaction database. Similarly for item set B, it occurs 3 times, you can see here and here. Similarly for item set C, 3 and D, which occurs only once, and transaction E, which occurs 3 times. So as we can see, the minimum support is 2, so this D item set is infrequent, so we discard D from the candidate item sets, and our frequent one item set is A, B, C and E with the support count of 2, 3, 3 and 3 respectively. So using this frequent item set of length 1, we generate the candidate item sets of length 2. That means AB, AC and AE, as you can see here in C2 table. Similarly BC, BE and CE, these are all candidate item sets of length 2. So we again go into the database, scan the database again and calculate their support count. Like AB, both items occur together only once in this transactional database, as AB occurs in transactional ID 30, and similarly AC transactions occur twice, like you can see here in transaction 10 and transaction 30 occur twice. And similarly we have calculated the support count of each candidate item set of length 2. As you can see, AB and AE have support count of 1, so that's why they are removed from the frequent item set, and our frequent item set is AC, BC, BE and CE with the support count of 2, 2, 3 and 2 respectively. So we are इस frequent 2 item set को यूज करते हुए हम जनरेट करते हैं frequent candidate item set of length 3, which is BCE. So remember this one, you people can see here is a big cut. Why? Because you probably see AC and BC as frequent. You might think ABC could be candidate item set of length 3, but AB is not frequent, as you see in this candidate item set of length 1. That's why we cannot consider ABC as frequent item set. So you may consider that A, C and BC are frequent, and then their superset is also frequent. So here is a problem. When we join these 2 item sets, we get ABC. So when we look into the candidate item set of length 2, we see that AB is removed as infrequent item sets. So that's why we cannot consider its superset as a frequent. So that's why it is removed. Similarly others. So we only get BCE as candidate item set of length 3. So from this we again go against the database and calculate its support count, which is 2. So this is our frequent 3 item set, or frequent item set of length 3. So this is an example of the a priori principle or a priori algorithm. So here we discuss some implementations of a priori algorithm. as we discussed in our previous example of a priori principle, we have discussed the self join and pruning concept. So the concrete implementation of this a priori principle involved two steps: the self join and pruning. Self joining goes like this. Okay, we get ABC and ABD. The first ABC and ABD, the first two are the same. BC and A and A, in both item sets the first item is same. So we can generate this self join and generate the candidate set as A, B, C, D. So this is the concept of self join. Means if the items occurs in two different item sets, we only write it one time. So when after that we need a pruning process. The pruning is pretty simple. Before you count against the database, you can see for ABCD, this BCD is up there in the frequent item sets of candidate item set of length 3. So we can consider its superset as the frequent. But from these two item sets of length 3, like ACD and ACE, we get ACDE as A is same here and same here, and we combine other two as the candidate item set of length 4. So but CD, but for ACDE, CD is not up there in the frequent item sets. Like ACD is the subset of ACDE. So if CDE is not frequent, then its superset cannot be frequent. So that's why we prune this ACDE, as you can see in this example, which is discussed in the same way as we have discussed. Okay, at the final we get only A, B, C, D as the candidate for frequent item sets. So we get only one candidate, which is ACDE. So once the frequent item sets from transactional database or from the transactional database D have been found, it is straightforward to generate strong association rules from those mined frequent item sets, where strong association rules satisfy both minimum support and minimum confidence. So this can be done using this equation of confidence, for confidence, which we show again here for completeness. The conditional probability is expressed in terms of item sets support count, where support count A union B is the number of transactions containing the item sets A and B, and support count of A is the number of transactions containing the item set A. Because the rules are generated from frequent item sets, each one automatically satisfies the minimum support. So frequent item sets can be stored ahead of each of time in hash table along with their counts, so that they can be assessed quickly. So we have to consider two things in our mind when we generate association rules from frequent item sets. The first one is, for each frequent item set I, generate all non-empty subsets of I. And the second step is, for every non-empty subset S of item set I, output the rule S implies I minus S. You have to keep in mind these two points for generating association rules from frequent patterns. So we consider this transactional data set, which contains 9 transactions, and each transaction has different number of transactions of different number of items in their respective transactions. So we have to use a priori algorithm for finding frequent item sets in this transactional data set, and then we have to calculate, or we have to generate association rules from frequent item sets. So this is the same as we have discussed an example in previous slides. So we just give you an overview and then directly go into the step of generating association rules from frequent patterns. So this is our transactional database, and we set the minimum support threshold to 2. We get these item set as candidate 1, item set I1, I2, I3, I4, I5, and their support count is 6, 7, 6, 2 and 2 respectively. So from this candidate item set of length 1, we can generate frequent item sets of length 2, of length 1. So as these all item sets fulfill the minimum support threshold value, so that's why these all item sets are frequent 1 item sets. So from these frequent 1 item sets, we generate candidate item sets of length 2 as I1, I2, I1, I3, I1, I4 and I1, I5. Similarly for I1, I1, I2, I3, I2, I4, I2, I5, and similarly for I3, I4, I3, I5 and I4 and I5. These are candidate item sets of length 2. Then we again go against the database and calculate their support count. As you can see, I1 and I2 occurs 4 times in the database. I1, I2, 1. Sorry, I1 and I2. I1 and I2, 2. I1, I2, I1, I2. So I1 and I2 both occurs together in this transactional database 4 times. Similarly for other item sets you can calculate. As you can see, we check I3 and I4. I3, I4, I3, I4. There is not even a single transaction in which these both items occur together, so their support count is 0. So that's why we discard the item sets that are below the minimum support value. So our frequent 2 item set or frequent item sets of length 2 will be this, which contains I1, I2 with the support count of 4, I1, I3 with support count of 4, I1, I5, I2, I3 and so on. So from this we can calculate candidate item sets of length 3. Similarly you can do this as we have done in our previous example. This is our frequent item set candidate item set of length 2 with their support count, and from this we can generate frequent patterns of length 3 and their support count is 2 and 2. So from this frequent 3 item set we can get candidate item set of length 4, and this candidate item set support count is only 1 because I2, I3, I4 and I1 occurs only once, and which is below our minimum support threshold. So that's why the frequent pattern of length 4 is an empty set. So we only get 2 frequent item sets of length 3, which is I1, I2, I3 with the support count of 2, I1, I2 and I5 with the support count of 2. So we use these frequent item sets in order to generate frequent items in order to generate association rules. So according to the rule of generating association rules, as we have already discussed, that we have to generate sub patterns of the frequent item set. So suppose we have considered this frequent item set, which is I1, I2 and I5. So what are the association rules that can be generated from this frequent item set? So the non-empty subsets of this frequent item set are I1, I2, I1, I5, I2, I5, I1 alone, I2 alone and I5 alone. So as you can see, if you remember this, if you remember this principle, that you have to generate S implies I minus S association rules. So let's go back into the slide. So for this subset, this is our subset and this is our item set I, frequent item set I. So this is S and this is our I. So how can we generate association rule? S implies I minus S. So I minus S, we get I5. Similarly I1, I5, which implies I2. Similarly for I2, I5, remaining part is I1. Similarly for I1, the remaining or the difference of Si minus S is I2, I5. And similarly for other two non-empty subsets. So how we can calculate this confidence? So we have to go back into the database, like you can verify these calculations from the transactional database. That means the confidence and the sport of these two, all these three items is 2. That means I1, I2 and I5, all three items occur together in the database only 2 times. However, the sport of this part, that means the I1 and I2, occurs 4 times. So that's why the confidence for this rule is 50%, and similarly for other rules. So if we set the minimum threshold to 70%, so what is the which rules are interesting ones, or what rules you may consider are the good rules? So here's only second, third and the last rule are interesting rules. Okay.